Hello, I'm Sena Kiciroglu, and I would like to present our work, ActiveMoCap, Optimized Viewpoint Selection for Active Human Motion Capture. The accuracy of monocular 3D human pose estimation highly depends on the viewpoint from which we capture the image. This paper addresses the problem of positioning a moving camera, such as a drone, at the location which will give the highest accuracy for pose estimation. An active motion capture system, such as one based on a personal drone, would allow one to film themselves performing a physical activity and analyze their motion, for example, to get feedback on their performance. Such a system is important because, when using only one camera, the quality of such feedback will strongly depend on selecting the most beneficial viewpoints for pose estimation. Existing works either perform 3D human pose estimation without selecting the viewpoint actively, or do not focus on optimizing for monocular 3D human pose estimation. Our contribution is an approach that aims to find the best next viewpoint to maximize monocular 3D human pose estimation accuracy. Specifically, given a short video sequence, we introduce an algorithm that predicts which viewpoints should be chosen to capture future frames so as to maximize 3D human pose estimation accuracy. From the current frame, we find the 2D and relative 3D human pose using off-the-shelf networks. The 2D pose and relative 3D pose of the last K frames is then used to optimize for the global 3D human motion. The next view of the camera is chosen so that we maximize a utility function designed to predict pose estimation accuracy. However, we cannot define the utility function in terms of pose estimation accuracy because doing so would require knowing the true person and camera position, leading to a chicken and egg problem. Instead, we use the uncertainty of the prediction as a surrogate for accuracy. Our key idea is to model the uncertainty of the pose estimation in a probabilistic setting. Let P be the posterior distribution of poses. Our goal is to find the uncertainty of this distribution P. We know that the energy we minimize during pose estimation, E pose, corresponds to the negative logarithm of P. If we can approximate P as a Gaussian, then the covariance can be found as the inverse of the Hessian of the energy function E pose. We sum the eigenvalues of the covariance as a measure for uncertainty. This value is computed for every candidate viewpoint. We perform two sets of experiments. In the first, we allow the camera to teleport to any of the viewpoints without any constraints. Using synthetic data with motions from the CMU Graphics Lab motion capture database, we demonstrate that our active motion planner achieves consistently lower error values than the baselines, and we come the closest to achieving the best possible error for these sequences and viewpoints. The random baseline also performs quite well in these experiments, as it takes advantage of the drone teleporting to a varied set of viewpoints. We compare the uncertainties we estimate for each candidate view with the errors we would have if we were to visit them. The largest triangle shows the chosen location. Lower values are in blue and higher values are in pink. We see that the uncertainties and errors are in general similar. We succeed in choosing locations with low errors. We also test on the MPI-INF 3D human pose dataset to show that our model transfers to real scenes successfully. This dataset includes 14 cameras placed at various distances to the subject. We show that we are able to outperform the baselines. The second set of experiments is to simulate realistic drone flight using AirSim, a drone simulator. However, for our method to work, we need a good estimation of where the drone will be in future frames. In order to do so, we have integrated a simple flight model into our system. Since our flight model takes drone momentum into account, the optimal trajectory result for a flying drone turns out to be constant rotation, which is very useful for preserving momentum. This is very reasonable since it allows the drone to sample viewpoints as far apart from one another as possible, while keeping the subject in view. We conclude that this is the best trajectory to choose for estimating the pose of a single person in the case of no obstacles blocking the circular flight path. Discovering the optimal trajectories where there are no obstacles is an avenue for future work. We have proposed a theoretical framework for estimating the uncertainty of future measurements from a viewpoint. This permits us to improve 3D human pose estimation by optimizing the viewpoint selection to visit those locations with the lowest expected uncertainty. We have demonstrated with increasingly complex examples in simulation with synthetic and real footage that this theory translates to closed-loop drone control and improves pose estimation accuracy. Thank you for listening.